Hello everyone. In the last video we were talking about what do you call it, the equivalence relation, and we basically covered we we covered most of what's important in there. However, we stopped at what is called the modulo. What is it called? So I've done a bit of research here and there just to get an idea of not this one. It's actually congruence congruence model. So to quickly go through this, so what this actually means is that it's part of the equivalence relation. In that sense, you have two elements that share some characteristics that suffices an equality and equivalence. So in this case, as you can see, the symbol here is what denotes the relation or the relevance. Sorry, the relevance, or as it's called, congruence model. Anyways, so this denotes the relationship, the equivalence relationship, and as you can see, A is equivalent to B on modulo of C. So modulo of C enables these two to equal each other. And they've done a pretty nice example, this Khan Academy, where um, so you can think of a circle, sorry, of a pie, and then you have different slices within the pie. So this slice is ones, twos, and threes, and fours. So these are the prime. So these are the modular results. So you could get a. So if you have a set of integers from positives and negatives both ends, say you take a set of numbers here and apply them to the pie, you would have grouped different integers based on their modulo value, their end result, sorry. So the result of the modulo. So in this case, let's imagine we're calculating for mod 5. Then the possible outcomes you could be having is 0, 1, 2, 3, or 4. So grouping together the 1s and grouping together the 2s and 3s. So if you take any two elements within the y, within the 1, for example, or within the 3, for example, then you can say that there is an equivalence relation. In that sense, they share the same results going through not an equivalence relation, but going through the modulo. And we'll get to say an equivalent relation, it has to suffice three main properties that we talked about in the last video: symmetry, reflexivity, and of course as transitivity. So when you go, like, for example, the congruence modulo, it just means that um, two elements share the same results upon a given mod of a given integer. And there are some other details that have been mentioned in this post, which are pretty detailed if you ask me. And one of the things is that this is important to differentiate between the equation, the equal sign, and the symbol here. Um, it just means that they have equivalent classes, and remember that equivalent classes means the end result is like the range for the function of the domain. Mod C tells us the operation was the type of operation that was applied to A and B, and uh, congruence modulo C uh, is basically what we call congruence modulo C. Yeah, so this is the symbol for congruence, which means the values A and B are in the same equivalence class, and this is the type of operation used opt for. And you can see that there's an example here. Say 26 is equivalent to 11. Now I'm not saying it equates to 11, but what this means is that there's a congruence relationship on C, and you can see that 26 mod 5 would yield 1, while 11 mod 5 would also yield 1, which at the end of the day, you're just getting But of course, saying 26 equals to 11 is not right. Unless you go 26 mod 5 equals 11 mod 5, then you're saying it right. Otherwise, you have to add a dash in there, in which you say 26 has how do you say it? There's an equivalence class between 26 and 11 mod 5 and congruence. I keep saying conjure. So when we have both of these, we call congruence modulo C. So 26 congruence modulo 5. Congruence modulo 5. Okay. And then there is this. So given these examples here in this paper here, just Khan Academy, there is this example insights into congruence modulo, in which it says that so assuming you have, so the modulo is basically the end result is can either be 0, 1, 2 until say you have, for example, 5, then the maximum number it would have is 5 minus 1, which is 4. If you go back here, this is the maximum number it could have. And this is basically some sort of a pattern being recognized. And if you take the numbers, all the numbers that will yield 1, all the numbers that you would deal 2, and then we could give these, so you'd realize that the modulo is actually an increment on each slice. So if you go like 0, you only have multiplication of the modulo being implemented. So you can see here. So assuming so C is the modulo, yeah. So the multiplication would be 1, 2, 3, 4, and so on and so forth. And it's assuming it was 5. So you get 0, and then 5 multiplied by 2, that's 10, and then 15. And if you take a look here, you can see that 5, 10, 15, and 20, and these are all multiples of 5, right? And if you go for 1, you just add 1. And then this one you add 2. And you can see here the modulo plus 1. For the negative, you just add negative to the... You just add negative before the multiplier. And then if it's 2, you just keep adding, incrementing 2. If it's 3, you keep incrementing 3s, and so on and so forth. So that's one way to obtain this is the formula. And you can see here that it's negative 2 plus 1 negative. You just go like, depends on the direction. And it's multiples of C. And there are several comments here in which, there were some examples here where the congruence, so if you have 5x congruence 2 mod 8, and it says solve for x, one way these guys tend to solve it is that, of course, you just divide by 5, and then you eliminate this, and then you'll have 1 over 5 multiplied by 2 mod 8, modulo 8. So if you try to apply 1 over 5 modulo 8 multiplied by 2 modulo 8, it's like the you get it's something they've done here, which was a little different. And one thing you may notice here in the title, it says journey into cryptography. And one thing, well, it's obvious that these subjects are more important to cryptography and stuff, but anyways, it's really good to know. I mean, we got stuck the last time when we started reading about equivalence relation. We got stuck on the modulo because basically congruence modulo, right? So that's that, yeah. So I'm not sure how. So I'm not sure if this because 2 mod 8 in this case. Sorry, I keep jumping between the subjects. But as you can see here, so for this one, 5x congruence to 2 mod 5 mod 8 is considered that 2 mod 8 is a single variable. And then if you subtract, so it's like you multiply the 5 by mod 8 and the 2 by mod 8. I think that's what they're doing here. So So this is you divided by 5 so that you would eliminate the 5 on this side, and then you will be left with 2 over 5 mod 8. It's just 2 over 5 mod 8. Now what I find a little confusing is that, okay, so x equals 1 over 5 multiplied by 2 mod 8, modulo 8. The modular inverse of 5 mod 8, I'm not sure why they took this separately. Modulo inverse of 5 mod 8. I'm not sure what's the deal with this one. Like, why didn't you just go 2 over 5 mod 8? Wouldn't that be, or is this only integers? I'm not sure, to be honest. But anyways, that's that. If ever we, I mean, I'm not sure if we really need this. Mod b goes, okay, modulo inverses b goes, that is the modulo inverse of a mod b. Naive method. Iterate through values 0 to b minus 1 for a. Now, I'm not sure if this is what we should be concerned about now. Modulo between two numbers. Yeah, I mean, there are several topics that you need to cover, but let's stick to linear algebra for now and just be on with that. Let's practice. So I've already done the first question, I guess. So given x, congruence negative 11 mod 8. So we know this is more towards. So we know it's mod 8. So we know 8. So we know the modulo is 8. So if which of the following chooses valid solutions for x? So which x could be x could be anything really. So mod 8. So if you are mod 8. So first of all, let's solve for negative 11 mod 8. So there's this tool I found, which I think was pretty nice. Negative 11 mod 8 would, okay, negative 11. What if we go 11 mod 8? 11 mod 8, that's 3. So anything that would yield 3 is the right answer. So we know that on the third, so that's the like c plus 3. So we know h plus 3, that's the normal one, h plus 3. So that's like 11. No. Plus 3, 2, 16. So if you try to visualize the pi, and then we could go like, what would yield the answer of 3? So 3, it has to be plus 3. So definitely 6 is not an option. This is definitely not an option. So 27 mod 8 has to equal to 27. Yeah, that's it. That's the right one. Wait a second. Did I say 11? Oh yeah, so that's right. And then 39. But the problem with 39 is that it's negative. So if we go like negative 39, that would be like, okay, negative 32. If it's negative 32, it's 32. Now at 46. 6. So it's definitely 27. incorrect selected. Why is that? So it's 27. We're saying mod 8 should yield to 3. Yeah, it doesn't work. Yeah, that's correct. That's wrong. Modulo 8. 27 modulo 8. It's congruent to negative. This must be 5 plus or minus some integer multiplied by 8. I've already solved for these, and this is the none of the above. What? So it's negative 11 modulo 8, right? So negative 11 modulo 8. What is going on? Multiplied by 8. Multiple of 8. This is correct. Then you could like go on 27 modulo 8. It's like 3, so I've done all of these. But try to how do you reset this? I'm not sure how do you reset this. I'm gonna go back to 1. So modulo 8 in this case, it's like we know what range this is. Negative 11 mod 8. Negative. In mod 11, if you apply it here, it's like just getting 1 minus C3, 3C or something. Okay. Modulo 11 mod remainder is 5. 11 mod 8. So the remainder is 5, which is what has been pointed out here. The remainder is 5. It's not actually 3. So what I've done, I know what my mistake was this. This is what my mistake was, but the actual result is this. It's minus 11. The remainder is 5, and none of these actually is 5. Close this. Okay. Refresh the page. Alright, so I already know the answer, so it's 27. None of the above, sorry. None of the above. Improved your answer. Of course, because I know what the answer is. Next question. So negative 4 modulo 3, that's like negative 4 modulo 3. 4 modulo 3, so it has to be plus 3. It's like 2. Plus 2 or minus 2. Okay, so 33 minus 33, that's 0, it's not what we're looking for. Minus 1, that's shared. 12, not it. 35 and 34. 35 and 34. So we got actually this and this. So 9 modulo 6. 9 modulo 6. 9 modulo 6, that's like 3. And then we could like, we could visualize it in the graph, so we know it's 6 and 9. So we know it's like the modulo is 6. Let's try it out. So it will probably be on the sixth slice. So if it's on the sixth slice, we know the 9. Could it be possible that the answer would be 9 multiplied by 6? Anyways, we can't really do much about it because the modulo of C, then we know the number of outputs, so C 6, so the number of slices would be 5, C minus 1, right? So that's so the maximum number model would be 5, but 9 mod 6 is 3, so we should be getting 3. So negative 28, not it. 24, not it. 19, 27, 19, 27, not it. 44, let's check this one out. So 44, incorrect selection. Why is that? 9 mod 6 is 2, right? 9 mod 6. Oh my god, it's 27. So there's 27. So it's like, okay, I got the idea behind this. So negative 7 mod 12, the maximum number would be 11 minus 7 mod 12. It's like 5. So what about minus 43? Just be getting a 5. Yep, this is the right answer. It's about minus 5. 7. 529. 5. 29. Both of these are correct. It's about 43. Not correct. Check. Let's work. 5 modulo 13. So we got 13, 5, that's like 5. Right. 5 modulo 13. 1 second, let me just like quickly see the graphs here. If you go like 26 mod 5, 26, number 26, the answer is 1. Anyway, so 5 mod 13, that's like 5, so we're talking about the 5s again. Minus 21, this is the correct answer. 5, 17, so this is the correct answer. And it is the correct answer. So we're done with the quiz, so that's that. And if we take a look at the equivalence relations, we could see so basically it's stressing that A congruence of B mod C is the same as A mod C, which equals to, so these are the same representations of the same notation that we're looking at here. So, and this is basically the formula we talked about. So it's some integer, not some integer, basically the index plus the modulo value multiplied by some integer. So this is 13 congruence of 23 mod 5. Then this is the these are different methods, different ways to actually present this, but yeah, this is the interesting one. It means divides, or is a factor, divides A minus B. Okay, and then it's saying here that it has to suffice 3 relations, and then you could do that simply a congruence of A mod C. That's basically reflexivity, and then you have the symmetric in which A congruence B mod C is the same as B congruence A mod C. If A mod C B D, there's a way to prove it. Reflexive property. It would yield the same results no matter what. And then this would also yield the same result, and this would yield the same results for the same category of numbers. Alright, awesome. Maybe we could do some examples if there are. That's that. So we're through with the equivalence relation. The next topic should be on so lower boundaries and upper boundaries. Yeah, let's look at upper boundaries and lower boundaries then. Alright, so every subset of R is a set of real numbers. We shall define the upper and lower bounds of a non-empty set S of real numbers. Upper bound of a set S of reals, what? Oh man, these are weird symbols. They suck. This is not a good source that intensively uses these. It intensively uses these notations. Like, oh boy, that's super crazy. But anyways, it shouldn't bother us now. What we should be concerned with is that what it looks like. Well, it looks like that the upper bounds and the lower bounds uh, is where the value equals to the element at hand. So the upper bound is when this value is greater, and the lower bound is when this value is smaller. Mm. It's like the range, not the range, the bounds of a range. Yeah, we could just teach this. Yeah, I have this prepaid. This is the second topic we should be acquainted with. Zorn's lemma. Zorn's lemma. Zorn's lemma is a result in a set theory that appears in proofs of some non-constructive existence theorems throughout mathematics. We'll state Zorn's lemma below and use it in later sections to prove some results in linear algebra, ring theory, group theory, and topology. In an appendix, we will give an application in metric space. This means Zorn's lemma is not intuitive, and some of the terminology in it may be unfamiliar, but after reading through an explanation of Zorn's lemma and then proofs that use it, you should be more comfortable. Let S be a partially ordered set. If every totally ordered subset of S has an upper bound, then S contains, oh boy, we have to go through the upper bound and lower bounds again. Zorn's lemma is quite visible in algebra, otherwise why would you state them here? I guess we'll have to look for a video, a decent video that we could use to fully understand Zorn's lemma. Alright then, I'll leave this for the next video. Alright, so it was pretty productive today, I guess. Even learned all about congruent modulo, and I should add the notes here. Congruence modulo, I've added this here. Yeah, and the result of the classes are given the symbol. It's like the range to the domain, which is when we stated earlier. So that's that. The next step would be the Zorn's lemma. Zorn's lemma. Yeah. Alright then, see you soon in the next video then. Cheers.